All right, so we've been talking about uh, energy, kinetic energy, potential energy, and in a few lectures ago, we talked about conservation of momentum and how we can actually look at inelastic collisions when two things collide and move away as one body. Uh, this lecture, we're actually going to talk about elastic collisions. So this is where two things collide and they actually bounce apart. So one may be at rest and another may hit it, and they might both fly off in the same direction afterward, or depending on their masses and velocities, two things could hit and then bounce back in opposite directions from each other. So this lecture is going to explore sort of that interaction. This whole lecture is pretty much just one big derivation of some equations that you can use. All right. So let's go ahead and define perfectly elastic collisions. So you'll remember we talked about at the molecular level, the chemical bonds making up an object act like tiny springs. So you sort of have this lattice type situation going on where you have, an atom, and then the spring is the chemical bond between. It's not an actual spring, but it essentially behaves like one. So in terms of elastic collisions, this is the case where the kinetic energy of the colliding objects is transformed into elastic potential energy in the molecular bonds. Okay, so we have kinetic energy during the collision is transformed into elastic potential energy in the molecular bonds. So you can imagine a step one here. We have a ball traveling towards some object, and we'll just say that this is the molecular makeup of the object. Okay, it's got obviously lots of atoms connected by springs or bonds, but we're just going to look at what's happening over here on the microscopic level. Okay, so this ball has some kinetic energy. The second part of this interaction, essentially what's going to happen is the object hits the other object, and you get this stretch in the chemical bonds. Okay, so we went from kinetic energy to elastic potential energy here. Okay, and then what's going to happen in the end, okay, as we can see here in the text, this elastic potential energy is then transformed back into kinetic energy as the objects spring apart. So then at the end, what we're going to have, this is ball going the other way after this molecular bond has sprung back to its original shape. So obviously we're looking at something that's like macroscopic, like a ball, and something like, on the tiny microscopic scale, but this isn't exactly how the physics works here, but it's a good representation of what's going on. It's a metaphor, if you will. So any collision where all the kinetic energy is transferred to elastic potential energy. So anytime when you have K go into elastic potential energy, and then all of that goes back into kinetic energy, anytime when you have this full transformation, that is called a perfectly elastic collision. So most real-world collisions, they fall somewhere between perfectly elastic and perfectly inelastic. So in the real world, with the basic mathematics we're using here, you just sort of have to decide which one it's going to be. And then, of course, your calculations may not be perfect. But the math models we use for now with the elastic and inelastic collisions, they do a pretty good job in most conditions. So perfectly elastic collisions must obey two laws, and they're laws we've been talking about. So conservation of momentum is one, and of course conservation of momentum is obeyed in any collision. Okay, so this is always going to happen. In perfectly elastic collisions, the conservation of energy is also obeyed. So we have momentum and we have energy. In our situation now with these perfectly elastic collisions, both are going to hold up. So do keep in mind that the mechanical energy before and after is purely kinetic. So you have kinetic energy going in, you have the collision happening, then you still have kinetic energy and no like gravitational potential energy or anything afterwards. Okay, so let's look at this example over here. So we have this before situation where ball 2 is at rest. So ball 2 has no velocity. So what's going on here is essentially ball 1 comes in. They do have this brief interaction, and you'll notice in the after. Here we go. You'll notice in the after they maybe. Wow. Okay. So you'll notice in the after they both leave with two different velocities, purely kinetic energy. Now, again, we have momentum conservation and energy conservation going on. So with momentum conservation, we have our initial stuff and our final stuff. And you'll notice here, there's no stuff for like M2, V2 initial. But that's because it's zero. All of the initial momentum is actually just coming from the first ball. Okay, so that's zero. We have our initial momentum here from ball 1. But then in the final stuff, we have that initial momentum being broken up in between two different objects. So initial just ball 1, final is going to be ball 1 and ball 2. So that's been divided between both objects. Same thing with energy. So we know that the initial kinetic energy coming in is 1/2 mv squared. Okay, this is just ball 1. But then the final look that we have here, we have that initial kinetic energy being divided between ball 1 and ball 2. So if you think about it, you'll remember back from like high school algebra, the whole like if you have two unknowns, you need two equations to solve for them. Well, that's the same thing here. We have two unknowns. So we have the first velocity of the first velocity of the ball, or the ball, sorry. We have the velocity of the first ball after the collision, and then we have the velocity of the second ball after collision. Okay, those are the two things you want to find out. Two unknowns, so we need two equations, and here are our two equations. So that's why combining these two conservation laws together will actually allow us to solve more problems. Now we can actually deal with any time we have two unknowns in this setup. Okay, so, oh, yep, that's just my point here. Just saying that, yeah, two equations, two unknowns. You guys should know that. All right, so let's think about deriving equations for final velocities for these two balls. And this is a specific example. This is important. With ball 2 being at rest. Okay, so only one of these balls has motion, the other one is just chilling. So first, let's determine the final velocity. Okay, yeah, let's determine the final velocities of each object. So let's start with the conservation momentum. This is the easiest one to solve for. Nothing's squared. You don't have any of those 1/2 terms. So here we go. Ball 1 in the beginning equals the momentum of the ball 1 plus ball 2. Now, all I'm doing here is just trying to isolate a final velocity. You can see I'm solving for this term in hopes of getting the final velocity by itself. Okay, well, that's just a simple dividing over by m1. You'll notice that when I do that, that just becomes 1 and goes away, and then this one just becomes a ratio. Okay, well, check this out. I have what I wanted. I have an equation that tells me what the final velocity of the first ball is. But look at what's going on here. To determine the final velocity of the first ball, I need to know the final velocity of the second ball, and I don't have that. Although my equation is set up to give me the answer, I'm still missing pieces inside. So let's move on to conservation of energy here. Okay. So from conservation of energy, we know that initial kinetic energy of the first ball equals the kinetic energies of the two balls later. Now I've highlighted here in green the velocity, the final velocity of the first ball, because I know that. I have an equation for it. Right? I have this equation that we just come up with for that final velocity of the first ball. So I don't know this in my equation, and I don't know this in my equation. Okay, so the whole idea here is like, well, we have two equations, or sorry, we have two unknowns, but let's substitute one equation into the other. Okay, so I'm going to substitute one equation into the other, and that's going to get rid of these two unknowns. Okay, so I do that here. I literally just plug in my equation from the previous column on the left. And now it gets gross. Okay, we have some algebra to do here. So here we have two things that are squared, or two terms in parentheses that are squared. So we're just going to break that up, and we're going to use the FOIL method. Okay. And now look at what happens when I do the FOIL method. Oh, good grief. There we go. So when I do the FOIL method, it turns out we actually get two terms that are the same. So we have this term that's been chilling outside this initial velocity. But after I do all my multiplication to FOIL this, you'll see I get three terms, just like you would expect. And notice the first term, which comes from, let's see, which comes from here to here. And then I distribute in my my constants out front. These two terms in red, they actually cancel out. So after you do the crazy algebra to get this final statement here, two terms just go away, and look at what you're left with. So we just have this stuff. I just rewrote it in a different order. I don't like having negative signs out front. So this is what we're left with. And we know this stuff equals 0. Okay, so, but here's the thing. Since we did that substitution, we only have one unknown now. Okay, and that always works when you have two equations, two unknowns. You plug in one equation, that removes one of the two unknowns. So now this really gross equation at the bottom, even though it's gross, we only have one thing we need to solve for now. And that's just the velocity of the second ball after the collision. So final velocity of the second ball. Now there's one more thing I'm going to do here. Move this. Okay, so in this step here, all I've done is essentially pull out the final velocity, the thing we're trying to solve for. But since this is a quadratic equation, you can see we have the thing we want to solve for is squared twice. So even though that's the case, totally fine. It means that we can pull it out once, but then it's still left over inside, which is fine. But we're going to have to do some clever mathematics to actually get V2F by itself. Because remember, that's what we want to solve for. Okay, so let's think about this. We have this statement. This is from the last slide. Okay, so nothing new. So let's do something clever. Let's actually use the zero product property. Which basically just says if you have two things, A and B, multiplied together and they equal 0, then A or B must be 0. Which makes sense, right? If you take 2 seconds to think about it, let's see, A times B equals 0. There's nothing you can plug into A and B where one of them isn't zero. If you get a zero out, you have to have a zero going in. So let's apply that here. Let's call this my A, and let's call this B. Okay? Because this is still just A times B equals 0. And we're going to use the zero product property here. So V2 final here on the outside where A is, if that's 0, well, that's a stupid solution. That's a trivial solution. That means ball 1 actually just missed ball 2 completely, and ball 2 didn't even move. Okay, so in this case, and this does happen sometimes in physics, sometimes you have quadratics where you get two solutions. One of them is either stupid or impossible, and you have to recognize that. And then you're forced to go with the other solution, which is correct and does model the real world. So this is useless because when the final velocity is 0, there's no interaction happening between the balls. Okay, so this is if A is 0. Okay, well, let's look at the other side. So if all the crap in the brackets up here, if that equals 0, okay, then what does that tell us? Well, if this equals 0, we are solving for V final, we can do some algebra. I won't worry about doing all that. You all can handle it. Essentially, we just want to get V2 final by itself. And after a couple of lines of algebra, you can do that, and you can get this statement here. Now, look at what we have. We have a statement where we have an equation for the final velocity of ball 2, which is totally one of the things we wanted. We wanted the final velocity of ball 1 and ball 2. We have this equation. Do we know everything in the equation? Let's see. Well, we know the masses, and we know the initial velocity of ball 1. Okay, so finally, it turns out we have an equation where we can solve for one of our unknowns, and we know everything in the equation. Okay, now we're good to go here. Let's figure out the V1 final. Okay, so this other unknown that we're after. Right? So let's go back to this equation where we almost had everything down, but we were still missing that one thing. Turns out the one thing we were missing at the very beginning of this problem was V2 final. Well, we have an equation for that. Now we can substitute this in back into our first original equation. You can see I've done that here. Okay, so now all I'm going to do is just distribute, turn the crank, do the math. Okay, we can walk through it really quick if need be, but essentially, let's see, we're just going to distribute this through. Okay, and this term shows up here. It's a little more simplified. Yeah, and then from here, you'll notice that this term and this term both have a V1 initial in them. So I pull them out. So that's where this 1 comes from. So this V1 is actually here. This term is still there. I've just pulled the V1 initial outside the parentheses. And then from here, I need to be clever. I want to combine these, right? So I essentially rewrite this as, because this is still 1, it's the total mass divided by the total mass. But by doing that, I actually make sure the denominators are the same. Okay, so I've got my denominators the same, which allows me to subtract these fractions, and I get a very simplified term here. Just the difference of the masses in the numerator and the total mass in the denominator. All right, so now I'm happy with this. I won't do much more to it. So I'm going to say this is my final equation. You'll notice that the denominators are the same. We have the total mass in both, which is pretty cool. Now we have these two equations that look very similar. We just have slightly different numerators, and we got what we wanted. We have an equation for V2 final, and we have an equation for V1 final. So now we know the velocities, the final velocities of both of these objects after they've collided with each other. Okay, so let's just do a quick example. So we have ball 1 with a mass of 100 grams traveling 10 meters per second collides head-on with ball 2, which has a mass of 300 grams and is initially at rest. Okay, so we got this here in our picture. So we have picture, let's label it. So we have the velocity is 10 meters per second. We know that this is going to be 0.1 kilograms. We know the second ball, which is not moving, is at rest. So that's 0 meters per second. And then we also know that it has 3 kilograms or 0.3 kilograms of mass. Okay, so this is our initial setup. Then we have the during, and then we have the after. Okay, so this is pretty cool. We only know stuff about the velocity of one ball, but here we're actually going to use 2 conservation laws and come out with knowledge about 2 different parameters here, which is pretty cool. Fortunately, we've already done this math, so we're going to use these pre-derived equations, these pre-canned, pre-cooked equations, plug in what we know, and then it turns out in the after situation, it turns out the first ball is actually going to go in the opposite direction, and then the second ball is still going to move in the positive x direction, so this will be negative. Which means our velocity down here in the picture is actually, this vector needs to be updated. So ball 1 is actually going to be moving, it's going to have a negative value, so it's going to be moving in the to the left. So this is going to be negative 5 meters per second. And then this ball 2 is going to fly forward at positive 5 meters per second. Now, remember that the velocities will not always be equal and opposite. That's just what happened this time, okay? Sometimes you'll have 2 different, very different values of velocity. Sometimes in this situation, it just so happens that they're the same. That doesn't always happen, so be aware. Now, let's think about the obvious situation that we haven't covered yet. So what if both objects have initial velocities? Okay, so you can see over here in this picture, we have this perfectly elastic collision in which both balls have initial velocities, here and here. Okay. Well, if we try to set up the equations, which you can totally do, you can do the equations, do the math just like we did in the previous slides, but it gets really gross. Okay, this becomes a really messy thing when both objects are moving in the before picture. So let's use something back from several lectures ago. Let's use a Galilean transformation. That's where if we have our moving reference frame, we can take these objects with velocities and rewrite their velocities in terms of the moving frame. Okay, you can think about it like if you're walking on a train that's moving and you're looking out seeing things go by, the things are going by kind of at the rate of the train speed plus your speed walking. And that's what we're going to do here. What we're going to do is use this trick and very much simplify this problem. So remember that the transformation goes from the lab frame, so the stationary frame, into the prime reference frame. And we do that right here. Okay, so remember that little v is the lab speed. So we're sitting here still. We see the speeds of the ball. This is the lab frame. Oops, lab frame. Okay, now v, big V, is the moving frame. Okay, so if we're going to shift all these velocities to be riding along in a moving frame, what is the speed of that frame? Okay, so the idea here is we're going to allow the reference frame to ride along with the second object. And all that means we're gonna duct tape this moving frame to the second ball and let it travel that way. So in our initial setup, I'm gonna switch colors. You'll see that this is our lab frame. Okay, Initially, these balls have the velocity of the first ball is 2 meters per second. The velocity of the second ball is negative 3 meters per second. It's heading in the opposite direction. Okay, well, there's our lab frame. I've wrote it in green. So now the idea is, let's take this moving frame and we'll have it move in the same speed and direction as the second object. Okay, well, the second object, its velocity coming into the situation is negative 3 meters per second, which means this reference frame also has to have a velocity of 3 meters per second. Okay, so that means our big V is going to be negative 3.0 meters per second. Now, the effect here, what's going to happen is essentially when we do this problem in the relative frame, in the moving frame, you'll notice we've labeled it here. Actually, I'm gonna leave this blue. So you'll notice we labeled it here as prime. Well, look at what this picture looks like now. Because our reference frame is riding along with ball 2, it's actually going to make it look like ball 2 is just chilling at rest in this reference frame. Now, since this second ball is just sitting there, all the mathematics is going to look like the previous problem, where ball 2 was at rest. We've literally shifted our coordinate system and translated it to make it look like the previous problem. But notice what that does to the velocity of the second ball, or sorry, the velocity of the first ball. See, it's not, this ball doesn't have a velocity of 2 meters per second anymore. It actually has a velocity of 5 meters per second. Okay, and you can actually, you can sort of see where that comes from. Essentially, if you're going to ride on ball 2, this ball 1 is going to be coming at you, it looks like, much faster than just the regular old 2 meters per second, because you're also heading toward it. So we can actually do this calculation pretty quickly, and I've got it written out here to make it a little easier for us to see the mathematics. So ball 1, okay, this is going to be the speed that we just talked about, which is now 5 meters per second. But this is y. Okay, so we're translating to the relative frame. Okay, and we have this initial velocity of 2 meters per second. So remember, that's our lab frame. And then we have the relative frame that we're being transformed to. Okay, so we know that the speed of the reference frame is negative 3 meters per second, because that's the same as ball 2. Okay, so let's just plug and chug. So we have our velocity of ball 1, 2 meters per second. Okay, this is VI minus big V. Okay, so that's the velocity of the relative frame. Well, minus a negative here just turns into a positive, so we have a final velocity for the ball, or an initial velocity of ball 1 as 5 meters per second. Okay, well, that goes into our equations that we just derived earlier. Okay, now we know that we know that initial velocity that we needed. Now we can calculate the final velocity of ball 1 because we know everything in the equation. And it turns out that velocity is 1.7 meters per second. Keep in mind, this is still in a relative frame. Okay, this is the velocity as seen from the one riding along with the second ball. Let's do the same thing for ball 2. Okay, so we have our Galilean transformation. We know what the speed of big V is. Let's plug this in. Okay, so this is ball 2, the initial velocity of ball 2, and then we plug in big V, and it turns out we get 0 meters per second, and that should be what we get. We want this to be 0 because this reference frame is moving along with that second ball, so there shouldn't be any perceived velocity difference between these two. Okay, well, let's see. Yep, so we're going to take this relative velocity and actually, hold on, I'm getting ahead of myself. Let's take a look. In this equation, we don't even need ball 2 anymore. Well, that's nice. Because remember, when we derived these equations, that the dependence on ball two's velocity just went away. Even though it's zero, there's nothing there. So I don't have to sit here and think about how to plug in the 0 meters per second. This is just showing that the reference frame and the ball are traveling together. That's all. Okay, so let's go to the second equation and calculate the final velocity for ball 2. So I'm plugging in this relative velocity, it's 5 meters per second, and then I get a velocity of 6.7 meters per second in the relative frame, okay? That's important to remember. So these two velocities we just solved for, okay? I've brought the mathematics along with us here. Here, same math, nothing new, don't worry about that. These two final velocities are still in a relative frame. We need to transform this back into our lab frame, okay? So all we need to do, like over here in our first equation, we just have to solve for V1 and V2. Okay, so I'm going to rewrite our equations. V1 equals the relative frame plus big V, same in both sides. Okay, so I'm going to take this relative velocity we solved for the first ball. I'm going to untransform this velocity. And you'll notice I go from, in the relative frame, I go from a positive velocity of 1.7 meters per second. I now go to a negative velocity, negative 1.3 meters per second. So if we're riding on the first ball, if we're riding on the second ball in the moving frame, it looks like ball 1 has a positive velocity. But if we're not riding on that relative frame, and if we're like standing there still watching this collision happen, it turns out that ball 1 actually has a negative velocity in the end. And then same thing with ball 2, we're going to plug in our relative velocity, v prime 2, and then untransform from the relative frame to the stationary frame. And then this one actually has a positive velocity. And you can see here, you've got an after picture of this collision with both of these labeled. Okay, so that's essentially this whole lecture was covering one specific type of problem when you have two objects colliding. How does that work when only one of them has an initial velocity? What tricks can we use when both of them have an initial velocity? And you can see it's fairly, I mean, the algebra is pretty heavy, but luckily there are some tricks that we can use to keep the math as simple as possible. So the big takeaway here is essentially when you do have the whole two equation, two unknown situation, you can actually employ both conservation of momentum and conservation of energy to solve problems like this.